Right, here we are back in the REPerformance engine building room with the main man Ricky.
The room of dreams.
The room indeed of dreams.
And cost loads of money to be in here.
So Rick, tell us what we've got lined up today for this this short video.
So I thought we'd run through rods and pistons, what we do, what the differences are, why we've gone the route we have, why they look the way they do, and then what we do is we're sort of putting everything together to build the engine. So for a long time we were dealing with CP Carrillo. They still do our pistons, but we've started dealing with we've been dealing with them a little while, a company called Arrow. They're British, and a lot of that came around with what's gone on this year, getting things shipped, and stuff like that. It felt a little bit better bringing it closer. They're up the road. I think they're like Northampton, I think. I've been dealing with the guys at Arrow on other projects for a while, and basically what we've done is we've brought our V10 engine programs for rods into Arrow to let them do our rods. So they've done us a new 5 litre piston and a new 5 litre rod and a new 5.2 rod. The pistons are starting to come across to Capricorn because ultimately that's who we sort of use to do our blocks. So again, the turbo kits are built in the UK. It makes sense that we use UK manufacturers to do our rods and pistons, you know, same as we use REPair, who are just down the road. So British is best. So what we have here is a 5 litre rod, a 5.2 Carrillo and a 5.2 Arrow. I even wrote down my little cheat sheet. The first thing to notice between the 5 litre and the 5.2s is the big end bearing face. Now, because it's an offset crankshaft on the big ends, how the rod interfaces with the other rod on the same bank is completely different now. So what we do is we have a large thrust surface. So if you look at the 5.2s, we've got a small oil relief on each one, but we've got a small thrust surface. And that one's bi-directional and that one is not. So the first thing you're looking for really is rods do have a correct way to sit on a crank. So there's always a relief, so to where the webbing meets the pin or where the webbing meets the journal. So you need to make sure you get the rod in the right way. But ultimately what that big, if you compare and look, oil on me, what this big surface is for here is when you've got two rods sat in the same journal and they obviously offset, because now they're doing this around each other. So you've got that lubrication surface to deal with it. So that's the first difference. The second difference is we do the small ends so that we can use them on stock pistons if we want to, which is why the two 5.2 rods are what we call parallel, and that's trapezoidal. So the stock piston in a 5 litre engine has basically the bottom of the piston is not straight where it sits the pin in. So we have to make sure we allow for that. Then we don't use rifle drilled rods. I don't like rifle drilled rods. So rifle drilling is where there's a hole up through the bottom of the big end that feeds a small end. I don't like them. I think considering where the most force is through a rod, all you've done is you've made essentially a big drain hole for the oil pressure to drop out the top of the rod. The theory being that it helps lubricate the small end. Well, actually, the majority of load is through the big end. You want that oil pressure in there, which is why if you look at them, they've all got drip feed holes in the top of the small end, so that when the squirter hits the bottom of the piston, it lands on top of the rod and it drip feeds through. That's how stock engines are, how they are OEM. So we've just kept that part in the rod design. They are tanged. in the big ends, so they can take a tanged bearing. And by a tanged bearing, if I have got one, I have, I'll pop you on Davey, is essentially that, the little piece that sticks out. That does not stop a bearing from spinning. All that does is helps locate the bearing longitudinally, or rather, if you lay it down that way, it helps locate the bearing the right height inside the rod. That's all it's for. People think it's to stop it spinning. It isn't. It won't stop the bearing spinning. The only thing that stops the bearing from spinning is the crush, which is when you've got the two bearing halves in and you clamp the rod up. That's what stops the bearing from spinning. So all of them, we use tangs. Some bearings have tangs, some bearings don't. The OEM rod bearings from the factory don't have tangs. You have to set them up right. But we design our rods to have tanged relief in them because the bearings we've had done by King, for example, in the past, they have tangs in them. So that's why we've got tangs. Then we go for uprated bolts. So the most, if you think under combustion pressure, the rod is pushing down on the crank. So actually, the strength of the bolt is for the other way. The strength of the bolt stops the top of the rod and the piston pulling apart when it gets to the top of the exhaust stroke, which is when it's in its unloaded state. So when you're on compression stroke, you're compressing, so there's a force there trying to slow the piston down. When you're exhausting, there's nothing there. So that's why rod bolt strength is there to stop the expansion of the rod from the cap to the piston. And if you think that piston weighs 284.6, it's not balanced, 284.6 plus a pin is 390, plus a ring pack is 410, and we use cram locks. That's 412 grams plus your small end weight, doing 9,500 RPM. That's what your rods are there to protect, or to deal with. Your rod bolts are there to deal with that force. Basically, trying to stop a piston, or trying to stop 412 plus small end weight at 9,500 RPM from trying to come out the top of your engine. So on an OEM engine, everything we do is uprated bolts. We don't deal with anything else. So they're all ARP, or in the case of Carrillo, Carrillo bolts, uprated bolts. Don't deal with any others. That's all we do. I don't see the point. Even when we do, say we do stock rods, we'll always uprate the bolts. So we use aftermarket uprated bolts on stock rods. Yes, we have to machine the rods, but that's just what you have to go through. So the correct way to tighten a rod fastener is stretch. So this is in a stretch state, so this isn't going to be right. But what you would do is, only because I haven't got a bolt out of a rod, I didn't think about that, is you'd put your rod, that way Rick, you'd essentially, with a bolt in your hand, out with the rod, you would put it in a stretch gauge, and you would then set your gauge to 0. Which would be like that. You would then put it in the rod, and using that device, so you can use a torque wrench, you would tighten the rod to stretch. Now normally they're between 5 and 6 thou stretch. So you've got your torque wrench on, and you set your torque wrench to what the manufacturer give as the max permissible torque. Say for example 60 Newton meters. You set your torque wrench to 60 Newton meters. You put your tightening little offset spanner on the bolt, and you pull on your torque wrench until you get the stretch you want, and you will just see your gauge creep round. And that's how you would do it. So that is how you tighten a bolt by stretch. When you get a data sheet and you see people just wanging a torque up onto them, yes, it's not the right way to do it. This is the right way to do it. That is why when you look in the bottom of an ARP bolt, you get the dimple. And the dimple is there to sit in the tool. So that's how we tighten all our bolts. It is an absolute friggin' nightmare. Because you can't, when you put the bottom girdle in, well, if I flip an engine over, I'll show you why. This will do. Actually, that's not too bad. The 5 crank is worse. But if you can imagine, you've got a crank sat in here with 2 rods, trying to get that tool, the ARP gauge, and everything in there to jiggle it all around and to get your measurements is a nightmare. So what we normally have to do is put the crank assembly in, hold it, put our rods and pistons in, because remember, you're constantly turning an engine over to get a rod and a piston assembly in, and then down through the crankcase onto your crank so you can get your cap in and do it up. If you've ever tried to juggle a crank in when you've put rods and pistons in the block already on a 4-cylinder and then try and juggle a crank in, you know how hard it is. If you've ever tried to do it with 10, you may as well not bother. So we do it that way. We put the crank in, do our clearances, put the crank in, tighten this loosely, turn it upside down, drop each rod and piston assembly in, flip it upside down, so we've now got all 10 rods and pistons sat on all our big end journals, and then take this back off. So we then have the clearance to tighten everything up properly. Maybe I'll do when I'm building one, maybe we'll do another video and I'll show you what I mean if you didn't follow what I was trying to say. It's just a process of getting it all in and getting it all in correctly, because remember, you've got squirter jet clearance, squirter jet clearance, main bearing clearance, big end clearance, which is why they call it dry build. You're constantly putting it together, taking it apart, putting it together, taking it apart to make sure everything's machined and all the clearances are right. Even down to, you build a rod, a piston assembly, you drop it in, and then your squirter jets sit. Make sure I'm doing it the right way. Squirter jet sits in the bottom like that. On an aftermarket piston, that will foul. That'll hit. So you've then got to clearance that squirter jet. Because if you don't clearance a squirter jet, the first time you run it, the piston will come down, it will just chop the squirter jet off. So there's all these things going on at the same time, and you've got a wraparound crankcase, so it just makes it a nightmare. So yeah, trying to torque a rod bolt bearing up, doing it the rod bolt up on a big end bearing is a nightmare, trying to do it the proper way. But it takes time, you do it right. So that's what those little bits do. Then we've got, let me put my pin, put it somewhere. Then you've got pins. So this is the little guy that takes all the combustion pressure happening on the top of the piston. That is what transmits it into the rod, ultimately into the crankshaft, and then out through the drivetrain. So again, on a stock engine, a naturally aspirated, where there's no view for upgrading, we would not use a tool steel pin. That's a heavy pin. On anything we're going to tune, we use an uprated pin. Yes, it's weighty. Yes, you have to think about your reciprocating mass. But if you start using a smaller pin and loading up the piston, what you get is pin flex. And you see it if you go and look at the Carrillo, do a load of good video, CP Carrillo, what happens when you get pin flex in a piston and what it does. So we always go for uprated rod bolts no matter what we do. Anything we tune is on an uprated pin, and then we use these. So they're called cram locks. Looks like a conventional wire lock, but it's got that offset on it, and that is for this little tool. And if you've ever tried to put wire locks in with a screwdriver, you might be fine on a 2-stroke, but if you've tried to do it, I done a C63 the other week, and I think they were 0.74 gauge wire locks. I nearly lost my fingers. So we use cram locks. So you can see how it looks when it's in the piston. That little tang just sits nicely in the relief, but also, rather than trying to get a screwdriver in to dig it out, when you want to remove it, the cram lock tool just goes straight in. So that's what we use. The pistons, there's no exhaust relief on them. There is an inlet valve relief. There's no exhaust valve relief because it's not needed. And there is a slight dish to these pistons, not a dome. So it is a DI piston. This is a DI piston. But we're dropping compression, which is why we don't use a dome. So we've gone to a dish. We then use a chrome top ring, which sits in the top groove. And we use our piston ring gap in tool over on the bench to do that. We then use a NITRIDED NAPIER-CUT ring. So this is our second ring. And by NAPIER-CUT, I don't know whether the camera will pick it up. If I just get something sharp out, Davey, so I can point. If you look at the outside bottom edge of that ring, you can see there's a groove cut into it. So that's a NAPIER-CUT. So that's a Napier second ring. That might be a better shot. Just there. That's a cut in the second ring. So it's just a little groove, and that's there to help support the oil ring. And then you've got obviously your oil control ring. The smart little bit these pistons have got as well is they've got drain backs to stop. So these are behind the oil control ring, and they just stop the control ring getting overwhelmed, and they allow it to drain back through to the underside of the piston. Nothing fancy. The smart bit for me is if you follow these two, they actually drain back into the wrist pin, so they help lubricate the wrist pin. So again, a nice little touch. They haven't let us down yet. They're bloody good pistons. So that is for an aluminium block, and these ones I mentioned in our last video that you need to coat. You can't run an aluminium piston in an aluminium bore without a coating. So there you go, that's the difference. Go facing that way. Coated, uncoated. Aluminium bore or standard bore, standard block, liner block. So that's the difference. And that is to stop the piston skirt galling on the cylinder walls. Exactly the same piston, one's coated, one's not. Same process, nothing changes in that respect. That's fine. And let's get that crank out of the way. And then this contraption is how you weigh up and match your reciprocating mass. They're normally pretty close. We normally don't have to do much modification. So on our big end weights, we would linish the underside of the cap normally, this area here, or linish the sides depending on what application we've got. That's where we would remove weight from a big end. On a small end, one of two things. Again, we'd either take it off the top of the rod here, or sometimes the underside of the support. You're talking tiny, literally that much just to get the weight we need. It's normally 0.1, 0.2 of a gram. But this tool is what tells you the weights. So I mean, if I take the rod off, and then just set my scales. Steady. We're back. Even Davey's camera got bored of me talking. So I think we just got up to rod weights. So the rods will come with a data sheet, and on your data sheet they'll tell you what they weigh, and we spoke about how we would balance a rod and how we would balance our reciprocating parts. But of course, at a point between the small end and the big end, it goes from being a rotating mass to a reciprocating mass. Rotate being it's turning with the crankshaft, reciprocating meaning it's going up and down the cylinder bore. So at some point there's that shift from one set of forces to another. But what we try and do is we try and balance out the rods. So we would do that by weighing our rod. So we would take it, we'd weigh it, see if it matched our data sheet. We would then take all 10 in this instance, and we would use this contraption. So this helps us weigh out our small end weight. So what you would do there is, I just do it on the fact that I've got a little spirit level. I'd put it along the line of the rod to make sure the rod was balanced across this centre to centres, and I would literally hang it on mine, and then you get a number. So in this point we've got 153.7 grams. Doesn't mean anything to anyone, but what it allows us to do is 153.7, nothing's changed. Lift it off, get another one. What have we got? $153.4. So if our rods are equal in weight, which I haven't checked, but if our rods are equal in weight, then we've got a difference in weight in our small ends. Now, you would sit there with your build sheet in your book, and you'd write all this information down, and then you'd make a choice on how you balance everything out. Does that weight need to be taken from the rod? Does it need to be taken from a piston? And you can juggle around what you can do. Sometimes, if you're fighting point 1, point 2, just moving pins around, get you your rod, get you where you need to be. So that's what is essentially known as blueprinting an engine. That's the process of writing everything down, having everything documented, and then coming up with the best solution for your engine. Remember, you want to take as little material off everything as you can. So if you can juggle parts of what you already have to get you close, then that's what you do. But that's essentially, if you see this, you know, you'll see it on other engine building videos on YouTube, that sort of thing. Banks Power, HPA Academy, that sort of thing. You'll see that. That's what it's for. You're figuring out how the balance of the rod is across all, in this case, all 10 rods. So that's what we got. And that is pretty much then how you assemble a bottom end, or how you assemble your reciprocating and your rotating parts. The big instance we haven't discussed is balancing your crank, and you do that by, again, weighing everything, getting all your measurements. And we don't have a crank balancer in house, we have someone else do it for us, and they bob weights and they spin it up, and they see how your crank is balanced based on what your rotating reciprocating part, or what your rotating parts are. But we don't have that equipment. We just don't do enough engines to sort of invest in that, so we outsource that part of the job to a good engineering friend who does it for me. But that's rods and pistons. There's loads more. The science behind it is huge, and there's loads more. But as a what we do, or sort of an entry into what we do, I think that sort of runs you through, you know, the little things we see, or the little things other engine builders see, and what you're looking for, why you're looking for it, why we use two tool steel pins over thin wall pins, why bottoms of pistons are different colour, what the holes are for. So hopefully it just tries to help people understand, if they don't know, what engine builders are seeing and why they see it and what they do, and everyone's got their little nuances of how they put an engine together. There's a lot of discussion, for example, around how you put rings on a piston, and when I say rings on a piston, I mean in orientation. So one side of a piston is going to be what's called major thrust, and one side is going to be minor thrust. But there's a science behind where that gap ends up. If you go and look at Ray and Morrison and what they say one thing. If you go and you follow other people like Marley and what they say and how you assemble their power pack pistons, they say something else. So there comes to be at some point a little bit of superstition isn't the right word, but that personal choice of how you do certain things. We've got our way of doing it, but it's there's rhyme and reason for everything, but there's so much science behind it, so much math involved. Ray and Morrison do some really good stuff on their website, some really good technical articles. They've stopped doing them now, but they were running a magazine over in America, and there's over 100 of those. They're really good. The HPA stuff is very good. There's information on the Marley website that's brilliant. So if you're really interested in engine building, there's a lot out there. There is a lot out there to go into that competition engine building textbooks, and it's
if it's something, sorry to interrupt, Bob, it's something that you're interested in, that you've pointed people in the right direction to look on YouTube and find a lot more about it.
Everybody started clueless, and that's no bullshit. There's a lot of fucking people out there that are amazing engine builders. Really, you've only got to go and look at Pro Speed Shop. Even over here, the people that are putting together AMG, PHH, the ones who build the Mercedes Formula 1 engines, they're in Brixworth. Mount Tune, all right, they're going through some trouble, but everybody working in those places started with no idea how to put an engine together, me included. I worked for a reputable engine builder. Everyone started at the beginning, but if you follow process, and that's what blueprinting is a process. Pages and pages and pages of information that are numbers. If you follow that process and you start simple, then anyone can be a world-class engine builder. Until you've tried it, you don't know. The really clever people, EFI University, Ben at EFI University, if you have a look at him as well, the really clever people are the ones who can sit there and work out. They know where they want to be and what they need to get there. It's not such a big thing here. If you think, for example, what the guys are pushing on GTRs, Golf Rs, TTRSs, even our engines, V10s, you won't really find many options for cams. You won't really find many options for crankshafts. Cylinder heads, not so much. There's a couple of boys in America who make their own heads, make their own billet blocks. But when you get into the LS7s and the LS3s and the big blocks and the small block Chevys and stuff like that, you can go through catalogues and there are hundreds and hundreds and hundreds of options. And that's where the good engine builders can look down a list of parts and go, right, if I buy that, and that, do my machining work, I'll end up with a really good engine.